thanks for all of you for sticking around for Friday afternoon. So yeah, I'm Cameron. I'm at Caltech, and I'm going to talk about 3 separate kind of related projects. One is my Trident code with my wonderful T-shirt here representing the brand. And the Tempest Simulations and the fire simulations, I've included some of the, not all of the collaborators on all of these projects, and in yellow I've included collaborators who are here today. So initially, I realize we've already had 2 CGM talks. I'll give super intro on the circumgalactic medium just to make sure everybody's on the same page, and then talk about some of these small scale effects and how it'll impact the overall CGM signal. So the CGM, as the name suggests, is just a low density gas that surrounds galaxies. It's usually optically thin, so we can't see it in emission very well. It probes a bunch of different things related to galaxy evolution, namely supernovae feedback, star formation, AGN feedback. So it's extremely important for understanding the behavior of this, and it might actually explain a lot of the dynamics and the change in the evolution of these systems. As I said, it's low density. In fact, it's so low density that you can't see it on this image. So we have to rely on background quasars or background galaxies to see it in absorption from the absorption lines that are present in the quasar spectra. Oftentimes these lines are lines like neutral hydrogen or magnesium-2 or oxygen-6 that we heard a lot from Xijing about. And these probe different phases of the gas. This is a density, temperature, phase diagram for the gas. And each of these, this is a wonderful plot taken from Jason Tumlinson, Molly Peebles, and Jess Work's review article last year. And it shows each of these ions probing a different phase of the gas. So there's an enormous amount of information that's stored in these spectra. And observers typically use the absorption line depths and equivalent widths and then put together radial profiles where you have equivalent width or column density on the y-axis and then impact parameter or projected radius on the x-axis. And you see that the column densities or equivalent width drop off as you go farther from the projected side of the galaxy. Now, when simulations, as was alluded to by Xijing, when simulations traditionally try to reproduce these radial profiles, we do a really crummy job. And these are a number of works in the last 5-6 years that have showed that the simulations underpredict. This is my work from 2013. The simulations are the line, and the observations of the COS Halos survey are much higher. So simulations really do a crummy job in reproducing the CGM characteristics. And I am going to attribute that mostly to small-scale structure and the lack of small-scale structure in the simulations that we've been trying to use to reproduce that. So when you think of a galaxy, traditionally you have much more spatial resolution in the interior of that galaxy because, well, you think of it in 2 ways. You either have a particle-based code like SPH, where your spatial resolution is tied to your particle density intrinsically. So you have higher density in the center of a galaxy, so you have higher spatial resolution. Whereas in the outskirts, you have really crummy particle density, so you have really crummy spatial resolution. Or you have grid-based codes using adaptive mesh refinement, where you're specifically triggering your refinement and spatial resolution based on density. So again, in regions of high density, you have very good spatial resolution, and in regions of poor density, like the CGM, you have very poor spatial resolution. And this is a problem because if you have structure where there's like a cold gas clump surrounded by a hot gas medium, and your resolution element is this big, then you're going to wash out that cold structure and it's just going to evaporate. And you're not going to resolve that in your simulations. So we really need to worry about resolving this structure in the circumgalactic medium to resolve the thermal instability. Okay, so yeah. So the 2 projects that I'm going to talk about, the Tempest simulations where we force refinement in grid-based codes, and then the fire simulations that most of you are pretty familiar with. So Tempest, in a traditional adaptive mesh refinement cosmological simulation where this is your projected effectively density, it's the neutral hydrogen density, your refinement structure might look something like this, where in regions of high density, you have high resolution, and then in regions of low density in the halo, you have very poor resolution by a factor of 8 or 16. In the Tempest simulations that I've been running over the last year, we forced the refinement to be substantially higher throughout the entire halo. We're still only achieving the same highest resolution in the disk, but we're forcing the halo to be at a minimum resolution. So we have this enhanced halo resolution technique. And the result is you find substantially more structure and you find substantially more cold gas because it allows the gas to fragment into thermally unstable cold gas and hot gas alongside each other. So again, this is H1. You can see a lot more structure in the case where we have the enhanced halo resolution relative to a traditional AMR run. And if we follow the evolution of this in a movie, because everybody likes movies, these are same run. This is with enhanced halo resolution. This is Redshift 2 now. It started at Redshift 3 for this movie. And as it progresses, you can see substantially more structure throughout the halo on the right side that you're just missing out when you don't have that resolution there. So finally, when it reaches Redshift 1, you can see, look, there's all this stuff out to 50 kpc that's totally not present in the low resolution case. So again, I know I wasn't here on Wednesday, but I heard my name was mentioned in the discussion at the end. So the work that Brant Robertson was presenting with Evan Schneider, where they have these Choya runs, where they explicitly do a unigrid resolution out to like 20 kpc, and they're resolving all kinds of really cool structure and cold gas that's being injected. That's only going out 20 kpc. I'm not pretending that this is going to solve all the problems, but this does allow for more formation of cold gas in the halo. I'm not changing anything about the feedback. I'm not changing anything about anything. It's just the resolution. It allows for cold gas to form in the halo and be ejected in the halo. Furthermore, if you try and compare this with observables, the H1 column density and radial, the impact parameter, the projected radius, this is essentially a heat map of where you tend to find those sight lines. And the white represents the median value. So there's a modest increase in the total H1 column density for these low ionization potential ions. And if you look at something like the covering fraction, this is for partial alignment limit systems, you see an increase by a factor of like 5 out to 40 kpc or so between using traditional AMR and using enhanced AMR, or enhanced halo refinement. And finally, not just does it increase the overall column density, but it changes the dynamics of that column density. This is a sight line going through a clump from Redshift 1 for the traditional AMR run, and then going through that same kind of stuff, but there's a lot more structure. And you see in the resulting spectrum, this is showing several different ions plotted on top of each other, neutral hydrogen, silicon 2, carbon 4, and O6. In the enhanced run, you see substantially larger columns, but you also see substantially narrower features because these are kinematically cold structures. And you just miss out entirely on that in a traditional CGM run. Anyway, so the point of this is enhanced halo resolution really increases the reproducibility of the observations. Do I think it's going to fix all the problems? No, but I think it's a push in the right direction that we need to account for before we're trying to do subgrid models or something like that. Okay, so enough talking about Tempest. The fire simulations. Cool movies. This is density on the left. This is temperature on the right. This is following an L-star halo. This is the latte simulations that Andrew Wetzel was probably talking about on Monday, but I missed it, sorry. So you can follow the evolution of this system as gas is channeled down onto the galaxy, and there's lots of star formation and outflows that are being ejected. Okay, but we can't actually see density and temperature in the sky. We have to rely on things like neutral hydrogen, or O6. So this is the evolution of those two ions for that exact same galaxy from redshift, high redshift to low redshift. You can see the H1 is probing colder, more filamentary gas, whereas the O6, just like Si Jing was showing in her movie, is probing more collisionally ionized and form a volume-filling gas that's usually typically 10 to the 5th or 3 times 10 to the 5th Kelvin gas. But it's much more diffuse. Okay. So with the fire simulations, they're a set of zoom simulations, so we don't have an infinite number of halos to probe. For this analysis, I've done this on 8 separate simulations from the fire suite. Shown here in green, this is stellar mass and star formation rate. And overplot, I've shown the COS halo sample, which is an observational sample at redshift 0.25 that was done in the last 5 years, led by Jason Tumlinson and Jess Work. So when I do this, I select these 4 galaxies because they seem to be in the center of the COS halos sample for the star forming systems. And when I try and reproduce without tuning anything, I just use those data and produce a the column density of neutral hydrogen versus impact parameter, and then the O6 column density versus impact parameter. We do a pretty darn good job of matching the observations. And this is one of the first results to indicate that we can actually match the O6. H1, we're doing pretty well in the interior, but we fall short of the observational sample in the outskirts, and I attribute this to the same thing I was talking about earlier with Tempest, and the fact that we don't have sufficient spatial resolution in the halo in order to get the low ion and the cold gas clumps that are structured there. But yeah, the fire reproduces the O6 at least, and most of the high ions like O6, nitrogen 5, neon 8. So if you look at the effects of resolution, there have been a number of different fire runs at different resolution, and you can see low resolution, medium resolution, and high resolution. As we increase the resolution, we're effectively doing a better job of resolving the structure and increasing the overall column density of individual ions. Now, this looks like it doesn't converge. There's an additional run that's been run, I think Andrew may have mentioned it, it's called triple latte. It's higher resolution than the latte runs that have been published. And it looks like it's converging, but it hasn't reached this redshift, so I've been doing some interim comparisons. So I think it's possible to trust these results because it looks like somewhere the convergence is between the latte runs shown here and the triple latte runs that are yet unpublished. If we look at the effect of halo mass on these profiles, you can see the black centroid represents these are like 5 times 10 to the 11th to 1 times 10 to the 12th halos versus blue, which is 1 to 2 times 10 to the 12th halos. And you can see a decrease in the overall O6. This is basically attributed to the fact that as you're going to higher and higher halos, your virial temperature increases, and so it falls outside the window where O6 peaks, which is about 3 times 10 to the 5th Kelvin. I can better show this again. This is the system. These are the set of the systems in our low mass, and this is the set of systems in the high mass. And this is the plot from Ben Oppenheimer's paper where he basically says that O6 is a virial thermometer, and as you go higher and higher in mass, you're dropping your O6 content because of this effect I just described, where the virial temperature goes too high relative to the O6 window. So we did, much like what Xijing was talking about, we tried to analyze how much of our O6 content was due to collisional ionization versus photoionization. So I did the same analysis using a collisional ionization equilibrium table for calculating the amount of O6 that was there, and that's represented here in blue. So this is again, the radial profile, the amount of O6 versus impact parameter for collisional ionization versus the total ionization. And when you look at a phase diagram, essentially what you're seeing is the collisional component sits at 10 to the 5th, and then there's a photoionized component that sits at lower temperatures and low densities. And it's primarily in the outskirts of the halo, but effectively what it means is that at least in the fire simulations, about 50% of the gas is in photoionized form and 50% is in a collisionally ionized component, which is, I don't know, it surprised me. I figured more would be in collisional. Finally, we look at the effects of including MHD in the simulations. It doesn't look like it's a dramatic effect between that and not including MHD, albeit this is not including cosmic rays. So based on Arena's work, it looks like cosmic rays may play a significant role. This is something that TK and Billy and a number of us are going to look at in the future. But in the absence of cosmic rays, MHD doesn't seem to make a dramatic impact. And finally, looking at the results of Shea, Garrison, Kimmel, who spoke earlier this week, he has these large local group analogs, and seeing if the environment plays a role in the total amount of gas in the CGM. It looks like there's not a huge effect in the O6. In the H1, it looks like there's a big envelope, a big H1 envelope in the cases where you have a local group analog, where you don't have that in isolated galaxies, but faring out into the CGM, it doesn't look like a very big impact. So environment and magnetic fields don't appear to have a huge impact on the CGM in the outer outskirts of the galaxy, the halos. And then I'll skip this for the most part. Trident is great. It's good for post-processing your data sets to look at CGM analyses, IGM analyses, making spectra. You can make cool movies like this. where you send a sight line through a bunch of stuff and you see the buildup of absorption lines as it goes through. It's all Python, it's all open source. It's going to be used for the Agora CGM comparison. It works basically, it's built on top of YT, so it works with basically every simulation code. And it's free, and we're awesome, and you will be awesome if you use it. So we have a bunch of new stuff, self-shielding, blah, blah, blah. So anyway, check it out. Here are my conclusions. Thanks.
Thank you. Time for questions. Michael.
So there's this interesting trend with the COS halos results that the non-star forming galaxies seem to have less oxygen-6. Do you think, based on your results with halo mass and what you showed from Oppenheimer, do you think that's because star formation is the quenching process is doing something, or is it purely those galaxies are in higher mass halos and so they tend to have less oxygen-6?
I think they tend to be in higher halos, but I think there'd be enough photoionization around the galaxy that it would be higher than what Fire's predicting, purely based on a collisional component. So I think there is something going on due to quenching that's changing it. I don't think it's purely a halo mass effect.
Hi. Two quick things. In the Tempest simulations, what have you looked at? What was the resolution you needed to get to in order to really start seeing a strong effect in the increase in the column density? And could you comment maybe in just one sentence how the Tempest runs compare to the Foggy runs?
Sure. So if you force the refinement to be substantially higher, if you are able to achieve something like 1 kiloparsec spatial co-moving resolution out to like 100 kpc, that's a bit of a threshold. Going higher, I haven't found convergent behavior. I don't expect to find convergent behavior based on the stuff that we saw from Brandt and Evan. So yeah, you can go as high as your computer will allow, but I'd say 1 kpc co-moving out to 100 kpc in the halo is a good start. In terms of these in the Foggy, similar technique, slightly different teams. They're primarily looking at high redshift. We're primarily looking at redshift 1-ish and lower. But the benefit of looking at high redshift is you can achieve much higher physical resolution because, yeah, it's at high resolution, or it's at high redshift. But similar technique.
I think we need to move on. So,
okay. Well, I'm around, so
yeah. So,
find the guy with the Trident shirt.
Yep. All right. Let's thank him once again.